Okay, in this video, we're going to be reviewing all the different types of factoring. We're going to go through each one at a time. First type of factoring that we always cover is factoring out a greatest common factor, which means simply doing the distributive property in reverse. Finding what's common. 24 and 54 have a 6 in common. There's a y to the fourth and y to the third. Always take, if there's y's in common, always take the lowest power. And this is going to be your GCF. And then we're going to put our parentheses, and we're going to ask ourselves, our GCF times what would give us each of these terms? So we start with our 6, and we say 6 times what will give us our 24 would be a 4. Then we count our y's. We need 4 y's. We have 3 on the outside, so we put 1 more on the inside. 6 times a negative 9 would give us our negative 54. We count our y's. We need 3 y's. They're all on the outside, so we're done. Next one, 51 and 17. Find your GCF, and you can actually divide and see, and you can divide both of those by 17. Then you take your lowest power, since they share a's, take your lowest power of a's, which is a to the third, and your lowest power of b, which is b to the fourth. That would be your GCF. Then you ask yourself, 17 times what would give you 51? That'd be 17 times 3. Now let's count. We need 8 a's. There's 3 on the outside. Let's put 5 more on the inside. We need 4 b's, and they're all on the outside, so we're fine. Notice that if you were to put another b, there's 4 now on the outside, 1 on the inside. That would give us 5 total. We only need 4. 17 times, if you need to put the 1, sometimes you might. Let's see if we're going to have to. 17 times 1 is 17. We need 3 a's. They're all on the outside. We need 5 b's, so we do need to put 1 more b on the inside. So we really don't have to put 1 b. We can just leave it as just b. So that's factoring out a GCF. Perfect squares. Your perfect squares are numbers like 1, 4, 9, which is 3 times 3, 4 times 4, 5 times 5, 6 times 6. Any of these values are perfect squares. 49, 64. We'll go all the way up to 100. That's 8 times 8, 9 times 9, and 10 times 10. And you can keep going with that list. Anytime you're factoring difference of squares, the rule for factoring here is if you have difference of squares, which means a perfect square minus a perfect square. Again, difference meaning minus, and a perfect square and a perfect square. These will always factor into what we call conjugates. A conjugate is identical except the plus minus sign. You put your x in your x, which gives your x squared here. You put your y in your y, which gives your y squared here. So x squared minus y squared will always factor in the conjugates x plus y times x minus y. So let's try that out. These are perfect squares. This is 6 times 6 and w times w. So this term is 6w and 6w. This is 5 times 5. So therefore, since this is subtraction, this is difference of squares. 2 sets of parentheses. Difference of squares factors into conjugates, so you can put your plus and minus. Ask yourself what multiplies to give you this will be a 6w and itself. What multiplies to give you 25 will be 5 times itself, and you're done. The next one is also difference of squares because you have the subtraction. 1/12 times 1/12 gives you this. R to the 6th and S to the 4th are also both perfect squares because R to the 3rd times R to the 3rd would give you R to the 6th, and S squared times S squared gives you S to the 4th. So therefore, 2 sets of parentheses. Conjugates, so plus and minus. 1/12 times itself gives you 1 over 144. And R to the 3rd S squared times R to the 3rd S squared gives you this term. Number 5. 4x squared times itself, 1 times itself, but this is not difference. So therefore, cannot factor. You can only factor difference of squares if it is a subtraction problem. It has to be minus between. 3 times 3, a squared times a squared, b times b. So this would be 3a squared b times itself. 10 times 10, c times c. So this would be 10c times itself. So that is, since it's subtraction, this is difference of squares. Factors into conjugates, so plus minus. 3a squared b times itself gives you this term. 10c times itself gives you this term. By the way, it doesn't matter which one's plus, which one's minus, since multiplication is commutative. Next up, sum of cubes. Okay, your perfect cubes. What do we mean by perfect cubes? 1 times 1 times 1 is 1. 2 times 2 times 2. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. 216, 343, 512, 729, 1,000, and those do also keep on and on and on. So if you're factoring sum, again, sum means the addition. Addition of perfect cubes. Here's your rule. A to the third plus B to the third will equal A plus B times A squared minus AB plus B squared. So what you got to do here, first identify, I'm going to leave my rule there. First identify if it is a perfect cube and a perfect cube. And one way you can factor it, I know h to the third is obviously a perfect cube. And 125, that would be 5 times 5 times 5. If you want to rewrite it in this form, then you can just take it in the place of a in your formula, put h. In the place of b in your formula, put 5. So therefore, you then have a plus b times a squared would be h squared minus a times b would be, again, a was h and b was 5, so let's put it as 5h, and then plus 5 to the second power, which would be 25, and that's factored. So just pretty much make the problem fit the form, and then just plug in each of the pieces. This is a perfect cube because that would be 2f times 2f times 2f to the third, plus 27 is 3 times 3 times 3. So in your formula, A is 2f, B is 3. So everywhere you have an A, put a 2f. So now we have 2f plus, everywhere you have a B, put a 3. Everywhere you have an A, put a 2f. Now careful, you got to square that. So square both pieces. That'd be 4f squared minus A times B would be 2f times 3, which would be 6f. And then everywhere you have a B, put a 3. So 3 to the second power would be 9. And there it is factored. Write it in the right form. This is 3a to the third because 3 times 3 times 3, a times a times a, plus 512 is 8 to the third, and you can check that with your calculator. So in your formula, everywhere you have an a, put 3a. Everywhere you have a b, put 8. So you have a plus b times a squared, so square them both, minus a times b, which would be 24a, plus b to the second. And number 10, same thing. Is this sum of cubes? This is 9 times 9 times 9. So that'd be 9 to the third, m to the sixth. That'd be m squared times m squared times m squared. So we can write it like that. We have something to the third plus 64 is 4 times 4 times 4. And n times n times n would give you n to the third. So here's your a, here's your b. So in your formula, you have a plus b times a to the second would be an 81, and to raise m squared to the second, power to power, you multiply, minus a times b, that would be 36, put them in alphabetical order, that would be m squared n, plus b to the second, square them both, gives you 16n squared. That is now factored. Number 11, now we're talking about difference of cubes. Now it's just a different formula. A to the third minus b to the third can be factored into a minus b, pretty much just the sign changes, times a squared plus ab plus b squared. So we're going to do it the same way, just plugging into a different formula. So now we have difference of cubes. So I'm going to write this as x to the third minus 343, that'd be 7 to the third. So in my formula, in the place of a, I'm putting x, in the place of b, I'm putting 7, because I have a difference of cubes now. So in my formula, I have a minus b times a to the second plus a times b would be x times 7 plus b to the second, and that's factored. Number 12, 125 is 5 to the third minus, I'm going to write 8 as 2 times 2 times 2, and then v would be v times v times v, so that'd be 2v to the third. So here would be your a, here would be your b. So in my formula, I have a minus b, which would be 5 minus 2v, times 5 to the second, plus a times b, which would be 10v, plus 2v to the second, which would be 4 and v squared. And that's it. 13, a couple more of these. 1,000 is 10 to the third. M to the third is obviously m to the third. Minus 1 is the same thing as 1 to the third power. So here's a and here's b. So my formula says I first do a minus b. A to the second would be 100 m to the second, plus a times b would be plus 10m, plus b to the second would be 1 times 1, which is 1. And then finally, my last one, p is already to the third power. I'm just putting it in parentheses to show you that's my first term. Minus 216 would be 6 to the third. Q to the third would be q to the third. So here's my a, here's my b. So factored form would be, first off, a minus b times a to the second plus a times b, which would be 6pq, put them in alphabetical order, plus b to the second would be 36q squared. That's factored form. Next up, factoring trinomials. Now here's your rule for trinomials. If it's a quadratic trinomial with a 1 out front, you write yourself 2 sets of parentheses, and you're asking yourself these questions. First off, the first thing in parentheses is going to be, what do I multiply? Let me scroll back up. What do I multiply to give me 1m squared? And that'd be 1m times 1m. That's the first thing in parentheses. Then you take these two numbers and ask, what two numbers, this will finish it, what two numbers add to give me this and multiply to give you this? I like to start over here with a 30. What numbers multiply to give you 30? If you need to make a list, 1 and 30, 2 and 15, 3 and 10, 5 and 6. However, the same two numbers have to add or subtract to give you 13. And I know these two numbers add to give you 13. So now we've got to get our signs together right. It must, and there's a problem there because it has to multiply to give you a negative 30. That means that one of them has to be negative, one of them has to be positive. So I don't think that's going to work. However, these two numbers also subtract to give you 13. And I can somehow configure it to where I need them to add to give me negative 13, multiply to give you a negative 30. That would be a negative 15 and a positive 2, and that does check out. You can always check this back by doing what we did in the last section and actually distributing that back out. If there is a number out front, first try to factor it out. If it won't factor, then we're going to have to use another method, which, by the way, this is not quadratic, but it is a trinomial of quadratic form. Since you have a fourth power, a second power, and no power, you can use the exact same method as long as this is double this. So here you go. This is where we use the slip and slide or the bottoms up method. Step number 1, if there's a number up front, if it can't be factored out as a GCF, move it to the end. We now have q to the fourth minus 13q to the second plus 36. We now factor like normal. 2 sets of parentheses. We have a q squared and a q squared that multiplies to give you q to the fourth. Now what two numbers add to give you this and multiply to give you this? And that would be a negative 9 and a negative 4. Okay, now here's the kick, or here's the trick. Whatever number you move to the end, you now must take both of these values and divide by that number. If it divides, great. If it won't divide, we're going to have to do something different. So the second one divides, so I have q squared minus 4 divided by 4 is 1 there. If it will not divide, we try to reduce what we have. If it will not reduce, this is where slip and slide gets its name. We slip the 4 to the end. Now we're going to slide it back up front. And we now have 4q squared minus 9. And that's your method of slip and slide to factor quadratic trinomials. However, let's look at something. This actually factors again. What you're left with is a method that we just went over. 4q squared minus 9. Let's come over here. That can actually, we can do 2 sets of parentheses and factor it again. This is a perfect square. This is a perfect square. Perfect squares factored into conjugates, difference of squares. 2q times 2q gives you 4q squared. 3 times 3 gives you 9. And the second one, q squared minus 1, is also difference of squares. Difference of squares factors into conjugates. Q times q gives you q squared. 1 times 1 gives you 1. So therefore, that's the complete factorization. You always see, could I factor it another step? Okay, another one of those, we have a 2 out front. It will not factor out because these are odd numbers, so let's move it to the end. You now have d squared minus 13d minus 14. 2 sets of parentheses. What multiplies to give you d squared? What adds to give you negative 13 multiplies to give you negative 14 would be a negative 14 and a positive 1. The number you slip to the end, you now divide by. If it divides, great. That'd be d minus 14 divided by 2 is 7. If it will not divide, try to reduce it. If it won't reduce, slide it back to the front. 2d plus 1. And you are finished. Number 18. No number out front, we can use regular factoring. 2 sets of parentheses. What multiplies to give you x to the fourth would be an x squared and an x squared. What adds to give you negative 1 multiplies to give you a negative 20 would be a negative 5 and a positive 4. Check since this is x squared still. Now let's always look and see, will this x squared stuff factor again? If it's only got 2 terms, all you can look for is it difference of squares? Now this is a perfect square, but 5 is not. So it's not difference of squares. Is it difference of cubes? Neither one of these are cubes. That's third powers. Over here, are these difference of squares? Now both of these are perfect squares, but it's sum. So therefore, that's as far as that will go. Always, again, if it's x squared, w squared, if it's still quadratic, see if it'll factor again. This one's suspicious. This might actually be a perfect square trinomial. Let me remind you of a trick that you can use to see if it is a perfect square trinomial. If you can take half of this and square it, and it's equal to this times this, 16 times 25, then it's a perfect square trinomial. Okay. Now here's your trick for factoring perfect square. Now you could still move the 16 to the end and do all that stuff. Perfect square trinomials are going to factor into something times itself. So you can just simply say what multiplies to give you this will be 4w squared and 4w squared. What multiplies to give you this and adds to give you the negative 40 or positive 40 would be a positive 5 and a positive 5. And you can multiply that back out and see. And we knew it was going to be something times itself. So that's going to be 4w squared plus 5 to the second power. And again, that could have also been factored with the other method, and I'm going to show it as well. So if there's a number out front that won't factor out, let's move it to the end. So I now have w to the fourth plus 40 w to the second. 16 times 25 when you move it to the end is 400. 2 sets of parentheses gives you w squared and w squared. Adds, multiplies would be 20 and 20. And you can see there it's something times itself. The number you slip to the end, you now divide by. If it divides, divide it. If it will not divide, let's reduce it. 20 over 16. That reduces by 4. Divide by 4 and divide by 4. And you get the exact same thing here. Once you're finished reducing it, whatever's on bottom, slide it back up front. So you have 4w squared plus 5 and 4w squared plus 5, so you can write it as a squared. So the slip and slide method, again, works on these. Number out front, it will not factor out. Move it to the end. You now have g squared minus 21g plus 90. 2 sets of parentheses. Again, this is slip and slide. You have g multiplies to give you 90, adds to give you negative 21. That'll be a negative 15 and a negative 6. I have the advantage of being able to pause this and actually think about those numbers. So it's not that I'm getting the answers that fast. The number that you slip to the end, let's now divide by. If it divides, go ahead. If it will not divide, reduce it. So 15 over 10, divide both of those by 5. You get a 3 and a 2. 6 over 10, divide both of those by 2, gives you a 3 and a 5. Those are reduced all the way. So now that we've reduced, now let's slide back to the front. The values on the bottom, the 5 and the 2, slide it back up front, and you get 2g minus 3 and 5g minus 3. And again, that can always be checked with FOIL or distributing. Okay, next up, factoring by grouping. Anytime you have 4 terms, 6 terms, 8 terms, always try to group them together. So with factoring by grouping, we're going to group our first two and our last two. We're going to try that to begin with. We're going to see common factors of this group. What factors out of 2h to the third and h to the second? 2 and 3, nothing. H to the third and h to the second, take the smallest power, which is h to the second. Factor it out of your first group, gives you a 2h and a minus 3. Ask yourself the same thing here. The only thing that factors out is a positive 3. When you factor it out, you're left with a 2h and a minus 3. If you get the same thing inside of parentheses for both groups, then this can factor by grouping. So what we do next is we take our first group and our second group and we factor out the stuff in parentheses. When you remove this from the first group, you're left with h squared. When you remove it from the second group, you're left with plus 3, and that will be your answer. Again, always check and make sure this h squared stuff, will it factor again? The answer is no. It's not difference of squares, or it's not sum of difference of cubes. Number 22, same thing. Two groups. First group has a z squared in common. Pull it out, you're left with z plus 7. Second group has negative 5 in common. Pull it out, you're left with z plus 7. Again, the stuff in parentheses are the same for both groups. When you pull the stuff in parentheses out of the first group, you're left with z squared. Out of the second group, you're left with minus 5. Since this is z squared, make sure it won't factor again. That is not difference of squares or sum or difference of cubes, so you are done. 23. Two groups. Pull a 3 out of 6 and 9. Pull 2 r's out of the r's, smallest power of r. You're left with a 2 and an r in our first term. You're left with a negative 3 in the second term. Second group, the only thing that is common is a 5. Pull it out, you're left with a 2r minus 3. The two groups have the same thing in parentheses. Factor that out, 2r minus 3, and you're left with, in the first group, 3r squared. In the second group, plus 5. This will not factor again because, again, it is not difference of squares or sum or difference of cubes. Two groups. First group has a 4 and 2 c's in common. Pull it out, you're left with c plus 5. Second group has a 9 in common. Pull it out, you're left with c plus 5. The two groups have a c plus 5 in common. Pull that out, and you're left with a 4c squared in the first group and a plus 9 in the second group, and that will not factor again. Number 25. We are now factoring completely. So we're going to combine every one of these methods and say, okay, factor it any way you can. Always look for a GCF first. So let's look at 25 and see, do I have a GCF? Yes, I do. 5 and 180 have a 5 in common. They both have n's. Take the smallest power. 5n times n to the fourth gives you the first term. Negative 36 gives you the second term. Then you say, okay, what can I do now? This is done. 5n will not go any further, so now we look at the stuff inside. It has two terms. So let's see, okay, is it difference of squares? Is it sum of cubes? Is it difference of cubes? And it's going to be difference of squares. So difference of squares factors into conjugates. Plus, minus. N squared times n squared gives you n to the fourth. Positive 6 and negative 6 gives you the 36. Now let's look again. Is this factorable? If it's two terms, is it difference of squares? Is it sum or difference of cubes? It is not, so we are finished. If this had been a perfect square, we could have went one more step. 26, three terms. Look for any common terms. Let's see, 6, 14, and 4, those are all even. Plus there's a negative in all of them, so let's pull this negative out to make it a little bit cleaner. They both have a 2, or all three have a 2 in common, and that's it, negative 2. Leaves you with 3k squared here, a positive 7k here, and a positive 2 here. This is done. It just keeps getting brought down in every step. The stuff inside is a quadratic trinomial with a number that is not 1 out front, so we're going to use slip and slide there. The negative 2 stays put. We're moving the 3 to the end. Let's try that again. So plus 6. Factor that as normal. The negative 2 just keeps getting brought down. That'd be a k and a k. A plus 6 and a plus 1 multiplies to give you 6, adds to give you 7. The number that you slipped, now let's divide by. So divide it by 3. If it's divisible, divide it. So you have now negative 2. K plus 6 divided by 3 is 2. If it's not divisible, try to reduce it. 1/3 is not divisible. It won't reduce. So therefore, slide it back up front and you get 3K plus 1. We know we're finished because this is not squared stuff. This is not squared stuff. It's now linear, so it will not go any further. 27. Look for common factors. There's a K in all of them, and that is the only thing common. That's your GCF. You're left with J to the 4th plus 3J to the 2nd minus 28. What you're left with, bring down the K, is a quadratic trinomial. Or actually, it's a quartic trinomial. But we can factor it like a quadratic because you have 4th, 2nd, and then no J's. So we're going to do J squared and J squared. Adds, multiplies will be a positive 7 and a negative 4. Now let's see if it'll factor further. Bring down the K. J squared plus 7. Is it difference of squares? Of course not, because it's plus. Is it sum or difference of cubes? No, because this is obviously not a cube. So J squared plus 7 will not do anything else. However, J squared minus 4 will. Difference, perfect square, factors into conjugates. J, 2, 2 gives you 4. Now we're finished. Number 28. Anytime you have 4 terms, we always try to group. Factor a 3 and a couple of S's out of the first group leaves you with a 5S and a 2. Factor a 2 out of the second one and you're left with a 5S and a 2. Both groups now have a 5S plus 2 that can be factored out. Factored out of the first group, you're left with 3S squared. And the second group, you're left with a plus 2. Since this is linear, s to the first power, we know it doesn't go any further. This is not difference of squares. It's not sum of cubes. It's not difference of cubes. So therefore, that doesn't go any further. Number 29. First off, something I like to do, and you can do this, it's legal. Since it's a positive 8 and a negative 27, you can flip-flop those around if you would like to. It's going to work either way. But look and see if there's any common factors. There's not. However, I noticed that this is a perfect cube. It's negative 3 times negative 3 times negative 3, and c times c times c. The number 8 is also a perfect cube. That is 2 times 2 times 2. So I can rewrite it like this, and I'm going to use my formula for perfect cubes. Since it is a sum, we are going to do the sum of cubes. So in this problem, my a value is here, my b value is here. So first off, we're going to do a plus b. So it's going to be negative 3c plus 2, which if you would have flip-flopped them, you'd have had 2 minus 3c, which looks a little bit better, but that's fine. You're going to square your a. That'd be a positive 9c squared. You're going to multiply a times b, and it'll be negative a times b would be a negative 6c. And a negative would be a plus right there. And then you are going to square b, which gives you a positive 4. Now, I about circled it. You can check to see if this, and that won't factor, that's linear. You can check to see if this is going to factor again. It's not going to. Anytime you're dealing with sum or difference of cubes, the quadratic never will factor again. Next one, we have a 6 in common. That's your GCF. We're left with z to the 4th minus 5z to the 2nd plus 4. The stuff inside might factor again. Let's try 2 sets of parentheses. Since it's a quadratic trinomial, z squared and z squared gives you the z to the 4th. Adds, multiplies will be a negative 4 and a negative 1. Now what you're left with again is z squared stuff. And both of these are actually difference of squares. Difference of squares will always factor into conjugates. So I'm going to have 4 sets of parentheses here. Conjugates here, z times z gives you z squared. 2 times 2 gives you 4. This one, conjugates, again, difference of squares. Z times z gives you z squared. 1 times 1 gives you 1. And every bit of this is linear, so we know it will not factor again. Okay, a couple more. The only chance that we have here is maybe difference of squares, or maybe even difference of cubes, maybe both. So let's try. Let's try first off. Now this one might take a while. Let's try difference of squares first. Let's see if 576 is a perfect square, because I know this is and this is. And if you take the square root of 576, you do find out it is 26. So 576 is a perfect square. So factor it by difference of squares, factors into conjugates. 3y to the third, 3y to the third. Wait a minute, I messed up on that first step. Always make sure, which would probably make this problem a whole lot easier, always make sure there's no GCF. Will 9 go into 576? And it actually will. So let's factor the 9 out first. You're left with a y to the sixth, and you're left with a 64. There we go. Now, that would have made things a whole lot easier, because now is 64 a perfect square? Sure. So bring down the 9. This is difference of squares. We have y to the third times y to the third, and that would have messed you up if you hadn't have done that. That plus and minus would be conjugates, 8 and 8. Now, this is what's going to make this problem long. This is sum of cubes. This is difference of cubes. So we're actually going to have to work this problem 2 more times using our sum of cubes and difference of cubes formulas. And there they both are. So let's try this. We're going to bring down the 9. And my y to the third plus 8. If you need to come over here to the side and say that's y to the third plus 2 to the third, you can. So there's your a value and there's your b value. Now let's plug it into our formula. So that's going to be a plus b times a squared minus a times b plus b to the second power. So now I'm done with my sum of cubes. Now let's move on to our difference of cubes. And luckily it's the same number, so I can just come over here and change that to a minus. Again, your a is y and your b is 2. So now you have y minus 2 times, we're using this one now, y to the second plus 2 times y plus 2 to the second, which would be 4. And you can see here, this would have actually, you could have done some difference of cubes here, and that would have been made things a little bit tougher. But do you notice that you actually have the conjugates here as well? So that's going to be factored completely. Once you use difference of cubes here, this is not going to factor again. That quadratic won't. So let's move on to the last one. And I see already there's a negative 15 in common. Lowest power of a is a to the first. Lowest power of b would be b to the second. Let's pull that out. Negative 15 times 1. I need 3a, so I have 1 on the outside, so 2 more on the inside, and I'm done with that part, so I really don't have to put the 1. Negative times a negative 4 gives you the 60. I need no more a's, but I need 2 more b's, so b to the second. This part is finished. Nothing else you can do with that. What we have on the inside is difference of squares. It will factor into conjugates. A times a gives you a squared. 2b times 2b gives you 4b to the second, and that is now finished.